I'm just reading here from this paragraph. We use diagrams in the last section to develop an understanding of vectors. Unless we have access to computer-aided drawing software like AutoCAD or SolidWorks, we can't get as accurate results by drawing these vectors by hand. So mathematically, vectors can only be added together when they travel in the same direction or opposite directions. So would you pretend with me that we're going canoeing? And I'm just going to kind of draw a picture of a stream. This is my stream. And the water is flowing in this direction. So we're in a canoe. This is my top view of a canoe, and here's our heads. Okay. And our paddles. All right. And so we're going this way, and we can propel ourselves, let's say at 3 miles per hour is how fast we can travel. But you know, I said over here that the water, hopefully I said water, was traveling this way. So we're paddling downstream, and let's say the water is traveling at a rate of 1 mile per hour. Well, in the end then, you would be traveling 4 miles per hour in total, because through your own gusto you can paddle at a rate of 3, but the water pushes you along at 1, and therefore you can go along at a total of 4 miles per hour. Let's say you turn your boat around and you go back. Now hopefully these oars are in whatever direction, you know. And now we're going this way at a speed of 3 miles per hour. But we still have this water to combat. So when we go upstream, when we fight the current, how fast do we end up going? Well, we'll take the 3 and we'll subtract the 1 because it's fighting us. And so upstream we'd be traveling 2 miles per hour, when downstream we were traveling 4 miles per hour. So of course we all like to go a little bit faster, and it feels like it's less work, of course. Well, that's why this kind of gives you an introduction as to why what we have to do next is we have to resolve a vector into its components so that we can get them to go in the x and y direction, so that we can add x components and then add y components, or subtract if they're going in opposite directions, like the current in the boat. So I'd like to make this called vector A, and its magnitude is 220. You know, we could even call it miles per hour, but it doesn't matter at the moment. But vector A. So I want to make vector A to be made up of, I'm going to drop a perpendicular line down to the x-axis. And this is not the parallelogram method. This is, I want to compose vector A to be made up of this and this vector, and they are called a sub x, or the x component, and this one's called a sub y. So like we drew in the last section, if you drew vector a sub x and then added a sub y to it, the result would be from the tail of the first to the head of the last, which is, the result is vector A. So I now want to take vector A and break it down into these two legs of a right triangle. Well, I gave you a 34-degree angle. So if I wanted to find the x component here, I would say that the cosine of 34 degrees is equal to the side adjacent over the hypotenuse. And then to find that x component, I'd move that 220. I'd multiply both sides by 220. And I'd get my calculator out and I'd calculate what 220 times the cosine of 34 degrees is. Oops, didn't mean that for that negative sign. And I'd find out that it's 182. That means the length of this line right here is 182. I'm sorry, I don't remember what the decimal value was. Next, I want to know what the y component of this vector is. And for this 34-degree angle, this is called the side opposite, and this is the hypotenuse. So it appears to me that the sine of 34 degrees would equal the side opposite over the hypotenuse, which is 220. And so again, to find the y component, I'd take 220 times the sine of 34 degrees. And if you did that on your calculator, 220 times the sine of 34, you would get the y component, 123. So the y component is 123. I should put the units on here because I chose to put units. So doesn't it make sense that this line looks like it's 123 and this line's 182 when this one's 220? And for that matter, you could try these two numbers in the Pythagorean theorem in your program that you've written, or you could take 182 squared plus 123 squared, take the square root, and it should equal 220. All right, so let's see what happens when we go into the second quadrant, third quadrant, and fourth quadrant. If I'm going to let this blue line be representative of a vector that its magnitude is 136 miles per hour, but I'm just not going to put that on there right now. So if I wanted to find its x, I'll call this a sub x, and its y, a sub y, components, I would do a similar thing, but this time I might be thinking about using a 75-degree angle because this is 180, and if I took away the 105, I'd have a 75-degree angle right here. That would allow me to use cosine again for the x component because this is the side adjacent and the hypotenuse. So I would say that the cosine of 75 degrees equals the side adjacent over the hypotenuse, and then 136 times the cosine of 75 degrees will be that itty-bitty number. Remember, if this blue line is 136, and then I'm going to tell you that that number is 35.2. But this vector right here goes to the left. That's bad. So our answer of 35 is not a good answer. We have to apply our own negative sign to the 35.2 because we visually can tell that this vector is in the second quadrant and that in the second quadrant x is always negative. I'm going to come up with a trick where we don't have to do that from now on, but I just want you to visually see. Using 136 times the cosine of 75 got us the right number, but not the right sign. This is called the side opposite of this 75-degree angle, and I was given the hypotenuse. So again, I'm going to go the sine of 75 degrees equals the side opposite, the y component of this vector, divided by 136. And then I'm going to solve this for a sub y, and I'll take my calculator and do the typing, and it's going to tell me that the answer is 131.4. Well, that's good. That one's positive, and it turned out positive, and it's supposed to be positive because this vector goes upward. So here's my two answers for this problem. And it's looking as though cosine is always used for an x component, and sine is always used for a y component. Now, why did it work for sine and why didn't it work for cosine? Here's why. In the first quadrant, all the trig functions were positive. In the second quadrant, only sine and cosecant were positive. So sine is positive here and here. And so because I used a 75-degree angle, which is in this first quadrant, it gave me a positive answer. But in the second quadrant, sine is also positive. Let me see, I'm going to look for some space here. I'm going to have to erase this now. We might talk about that a little bit more in class. But I'm now going to share with you that from now on, if you wanted to find the x component of a vector, you could take the magnitude of the vector times the cosine of the angle. Look, that's what we've been doing. Magnitude times the cosine of the angle. But the angle could be the angle that's in standard position. Standard position, remember, means an angle that starts from this x-axis and rotates clockwise to this 105 degrees. So if you would type 136 times the cosine of 105 degrees, it gives us the negative sign. So we got an answer before of 35.2. By using the 105 degrees, I get the negative sign because in the second quadrant, cosine is negative. But for the y component, when I take a times the sine of theta, again, theta in standard position, so in this case, 136 times the sine of 105 degrees, you get the positive answer you got before. I might have typed, let's see, 136. Hopefully oh, here it is, 131. 131.4. Same answer I got when I used the 75-degree angle. Again, that's because sine is positive in the first quadrant and the second quadrant. So, bottom line, let's just go ahead and do the next problem. Let's just say that this vector, its magnitude is 317, and if you get a quick visual of this, its x component would go to the left, its y component would go down, but I'm just telling you that the x component could be found by taking 255, oh I'm sorry, that's incorrect. The magnitude of the vector is 317 times the cosine of the 255-degree angle. So this is 255 degrees. The magnitude of the vector, let's call this vector A, is 317. So 317 times the cosine of 255 will give you the x component. It will give you a negative number. And 317 times the sine of 255 degrees will give you a negative number as well. And those two numbers are, for x, a negative 82, and for y, a negative 306.2. And the reason, again, the reason for that is in the third quadrant, the only trig functions that are positive are tangent and cotangent. So when you go use cosine and sine in this quadrant, again, this is the third quadrant, they're going to give you the negative answers, the appropriate, this negative 82 and this negative 306 that makes up the hypotenuse of 317. I'm going to stop, and I think I'll leave this video at that and let you, actually I'm going to go ahead and write down the answers for this one. Do I have the answers for this one? I'm afraid I don't, so I guess I won't.